Hi, my name is Ali. The demo I have for today is a partnership we had with THP through Dr. Fine, where we're basically building a drift detection and performance monitoring scheme for like the purpose of disease classification using chest X-rays. So just a bit of background: medical imaging is a highly dynamic data environment. So the change in, say, devices, protocols, the proportion of patient populations, as well as, say, new pathologies is very common. And being able to audit model performance during deployment is essential. The only catch is that ground truth labels in radiology are expensive, and there's usually a considerable amount of lag and effort required to collect and curate the labels. So the use of a methodology that leverages, say, in particular, chest X-rays like a standardized format, which are very abundant and almost immediately available. So being able to monitor, say, image-based data drift to provide real-time visibility of shifts over time to be able to alert practitioners to, say, the kind of data drift that might compromise model performance would be a very useful tool. So this is kind of like an overview of the monitoring pipeline that we set up for THP, just an experimental workflow. So just basically 2 sample tests using the chest X-rays. But first, we pass them through a dimensionality reduction technique. We either use a variety of techniques. Some of them sort of work best, but we use the TorchXRayVision library that has a lot of pre-trained models that are capable of reducing dimensionality of chest X-ray images. And we also use scikit-learn with the standard dimensionality reduction like PCA. And once you reduce the dimensionality, you do 2 sample statistical tests using the source and the target domains as defined. And we roll through like a set of univariate and multivariate tests to sort of find the right pairing between dimensionality reduction techniques as well as statistical test methods. So moving on to the data, basically, if you break the data down, it's 3. So in order to aid the study in terms of structuring the study of what we're doing with the chest X-rays, we sort of break down the data into 3 distinct periods of study, where we define a control period, a pre-COVID period, and then a COVID period, which consists of, say, March 2020 onwards. So there's around 50,000 chest X-rays for each period, and they also come with, due to the DICOM standard, they also have a degree of metadata associated with them, like the institutions at Credit Valley Hospital or Mississauga Hospital, the patient's age, gender, whether they're emergency or inpatients, the device that was used to create the scan, as well as other attributes like whether they're in the ICU, things like that. So the first thing we start with are a series of sensitivity tests to test pairings of dimensionality reduction techniques and statistical tests. So we use 2 domains for source and target. We use control and pre-COVID, and then we have another set of drift experiments for pre-COVID to COVID. So just establish like a control and then like a shift due to COVID. So we do 5,000 samples from the source domain and a series of increasing samples from the target domain, sample 10 times over, to generate like a mean and then an overlay of the standard deviation of p-values. So what we saw from the experiments was that trained autoencoders from the TorchXRayVision library, as well as maximum mean discrepancy, which is a multivariate test, had the best trade-off for sensitivity. And whenever we tried univariate testing like Kolmogorov, Smirnov, it was particularly sensitive to the high number of dimensions from the trained autoencoder, which comes in at around 512 dimensions. So one particular plot that was pretty important for the study was when you look at the p-value for pre-COVID to COVID domain, and you overlay it on a plot of control to pre-COVID, so that's the blue line, and then pre-COVID to COVID is the orange line. And we sort of use the best test we have, which is the trained autoencoder with MMD. So we see this trend in particular with the pre-COVID to COVID shift, where it falls below the green dotted line, which is just the line of statistical significance for the p-value, so below 0.05. And it falls below that line with almost an order of magnitude less data than the control to pre-COVID region. So you can see that there's a distinct shift due to COVID, since the detector is particularly more sensitive to target samples that come from that distribution. And then in sort of an extension to those experiments, we thought that explainability would make sense, in the sense where you take the same experiments going pre-COVID to COVID, and instead of doing like an unconditional sensitivity test, you do a conditional sensitivity test based on the metadata. So for instance, these two plots show the control line, which is the orange line from the previous plot for pre-COVID to COVID. And then you see the orange line represents for each plots whether the patient is an ICU patient or not. So for the plot on the top, you have a false, is ICU is false, so they're not an ICU patient. And then true for they are an ICU patient. And you can see a considerable, again, similar to before, a considerable shift in the number of samples it takes to produce a statistically significant shift. So you could say that the metadata category for is ICU equals true correlates well with the shift going pre-COVID to COVID. And similarly, for somewhat of an unexplained shift is the difference between the institutions. So for Credit Valley Hospital, you have basically, it hugs the control line pretty much perfectly. So you could say that it doesn't contribute as much to the COVID shift. When you use an institution like Mississauga Hospital, you see that there's a considerable dip well below the control line. So it's statistically significant, well below, like with less samples than the unconditional distribution. And so with all those tests combined, basically our next steps for the project are to expand the explainability of the drift detection. So trying to find ways of performing synthetic shifts. So basically having a way of testing how sensitive the detector is to like a degree of different shifts while you control other categories. So you make sure that the categories themselves are stratified, and you ensure that you can conduct these controlled experiments for like particular shifts that you're interested in, and then testing the detector sensitivity to those. And then also another very important thing was applicability of the drift detection. So simulated deployment, where you have kind of a sliding window of detection for continuous deployment of a detector with a set of thresholds for when it sort of alerts the practitioners to a shift. So being able to do hyperparameter tuning for the threshold and the test calibration on this kind of rolling window that imitates how it would be deployed in the real world was also another direction for the project. And also coming to the Cyclops framework, which is a big project we're working on, where we want to have support for drift detection on chest X-ray images. So a lot of the experimental workflow and reduction techniques I use for the THP work, we're planning on pushing into the Cyclops framework to make a pretty like easy API. So for instance, in the image below, you can see like the input shape for a small subset of images is 400 images, and then you have a height and width of 224. You can see in say 3 lines of code, you're capable of calling the trained autoencoder from the TorchXRayVision library, and then immediately transforming a map style dataset, like just a simple PyTorch dataset, and having it produce a set of reduced dimensions, so like 400 images, and then dimensionality of this 512 dimensions. And it also spits out, say, an optional number of labels for the image if those are available as well. So yeah, that's would basically be it. Thank you. If there's any questions, I'll take them now.
Hello? Okay.
Hi.
So I have just like a quick question. So I'm a little unsure of how, like the kind of the pipeline for the experiment. So you mentioned the train autoencoder and then also the dimensionality reduction. So first of all, what was the actual dimensionality of the images? And then was this trained autoencoder used in order to make sure that dimensionality reduction was not hurting the amount of information in the images before and after? Or I'm not like 100% sure of why that was used, or like how that really helps with detecting drift in this case.
I guess it's something like because if you compared, say, PCA to using the trained autoencoder, I guess I should have mentioned the trained autoencoder is trained on open source chest X-ray data. So having like a trained autoencoder that's capable of compressing things that are in the same domain as what the kind of data we're dealing with seemed like a smart direction to go in versus, say, training a PCA on each image in particular. That just seemed intuitive in a way. And also you mentioned about the dimensionality. So I guess the image below kind of shows you what kind of dimensionality we're dealing with. So the trained autoencoder will accept images of about 224 by 224 in the standard scheme for like ImageNet training that's common for convolutional neural networks. So I guess that would be almost, it's almost like a million dimensions, I think, in terms of like if you flattened it out into a single vector. So yeah, that's basically.
Oh, okay. So it's like, I guess the dimensionality reduction is more like just to standardize the actual input size so that you can put into like the pre-trained autoencoder thing.
Right, exactly. Well,
okay. So then from the pre-trained autoencoder, like maybe you get like your samples of the X-ray that you actually want to try to detect drift on. So how would you do that from the output of that autoencoder?
oh, sorry, I should have mentioned, it's not the output of the autoencoder, it's the bottleneck. So
okay.
The reduced dimensions of the autoencoder. So that 512 number is basically, you take the feature map, you take the mean value across the height and width, and you get a single feature vector out of the model.
Okay. So then in that bottleneck feature space, so how would you detect drift in that case?
Well, in that case, once you have like a reduced dimensionality, then there's basically these statistical tests where if you look at the diagram on the top right, you can kind of see once you've reduced them to these feature vectors, then the statistical tests just sort of take the vectors themselves and they perform. In the case of MMD, I guess I could have explained the concept in particular more, I guess, more detailed way of explaining it, but it's basically a way of detecting shift using a set of feature vectors from each image. So you have like a source set of images. So like the size of that would be like, say, 200 images by 512, the dimensionality of the reduced data. The reduced dimensionality, the chest X-rays that have been dimensionally reduced. So you have like 200 images by 512, and then you have the target distribution, which is 200 images by 512. And then you perform those multivariate tests, let's say MMD, or even univariate tests, which take just basically the distribution shift across the source and the target domain.
Oh, okay. So I guess you just do a statistical analysis across those like pre-COVID, whatever periods, and then just compare them to see, I guess, how they stack up against each other to try to detect drift.
Yeah, you basically choose what your source and target are. Based, in this case, it was pre-COVID to COVID in terms of like a time series based analysis. So like two domains in time are what we chose to do.
Okay, awesome. Yeah, that makes sense. Thank you.